Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Now, we talked about the range, which was the distance between the min and the max, but we may also want to break the data up into groups. A frequent one is to break it up into quartiles, meaning we're going to break the data up into fourths. So the first quartile is the score where 25% of the data is less than that number. The median is the middle, so that would also be Q2 for quartile 2. The third quartile is halfway between the max and the min. That's 75% of the data. And the max would be Q4. Each of these contain roughly the same number of data items, and they each contain 1/4 of the data. Now we can make what's called a box and whisker plot using that data to give a graphical representation of the spread of our data. Box and whisker plot looks like this. The box goes from Q2 to Q3, and this line in the middle is our median. And these points in the end are our min and max. So this is the box, and these are our whiskers. So this is the middle data. So our data on the above the median was a little bit more tightly collected or tightly dispersed, and on the bottom end we were more spread out. Now you can use the graphing calculator to do this. Now we can get these numbers for it to put on the number line here. The min is the 27 here, max is our 95, this boundary is Q3 85, 55.5 exact, and our median. You can also have the graphing calculator graph it. To do that we have to turn on what's called stat plots. So I press the second key and y equals, and I have to turn my statistical plots on. So I'm going to press enter here and turn it on. And you've maybe used scatter plots before, but now we can use this item here. Whoops, I skipped it. The fifth one over, that is a box and whisker plot, and we're going to draw the plot for the data in list 1, which is where we put our data. Now, if I graph it at this point, I'm not going to see much because my x-axis needs to go from about 20 something up to 100. So I have to go into window and I need to set my x. So let's cover the scores that could be on the test, 0 to 100. And x scales tells where the tick marks will be. So let's set that every 10 units. And now let's press graph. And again, we can see the box and whisker plot for our data. Again, we can see how spread out the data is. Sometimes we want a finer view of where data lies. Sometimes we use percentiles, or sometimes deciles, which would be every 10. So a percentile, whatever the number is the value in the table where that percentage of values are less than or equal to a particular number. So if we wanted to know what score would be the 90th percentile, there were 29 scores in the table, so 90% of 29 is approximately 26. So we would be looking in our ordered list of data the place where there would be 26 scores less than or equal to a particular number, and that came out to be 93 in our data. Again, you have to use your ordered list of numbers. So if we go back to our stem and leaf plot, we're looking for 26 numbers to be equal to or lower. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. So this represents a 93. That's the 90th percentile, meaning 90% of the scores were equal to or less than that score. So if you were the one that 93, you did equal to or better than 90% of the people in the class. Another frequently used measure of the spread of the data is called standard deviation. It measures how the data is dispersed or how it's clustered. We use the symbol, the Greek letter sigma, to represent standard deviation, and that's for an entire population. Now we use this summation symbol in our last video. So that's what this is saying, is that we're going to take each point in the data, each data item, and subtract from it the mean. So we're finding the distance from the mean of every item and squaring that number, and adding all those distances up, and then dividing by n, and then taking the square root. If we were dealing with, say, a sample of a large population and we do not know the standard deviation of the whole population, we can calculate a sample standard deviation to estimate our population thing, and we use a similar formula, but we divide here by n-1. It gets into a topic of statistics called degrees of freedom. For today, we'll use this sigma. What's important is not so much how we calculate it, because we'll be using the graphing calculator to calculate that. So if I go back to my data, I can't go up, so let's just recalculate our data here, our stats. Again, for our test scores, it was about 19.6 was our standard deviation. Now, when we're dealing with large populations of data, well, first, before we do that, one of the things we have to deal with, so I just showed you how we calculated the sigma. We just showed that there. One of the things we have to deal with in statistics is something called outliers. Outliers are potentially anomalies. Maybe there was some error in the data collection. Maybe we recorded a number wrong. Or the data could be valid data and it's just a rare case. Statisticians, to avoid these outliers from significantly impacting the data, frequently a statistician will throw out the outliers. So instead of subjectively deciding on what's an outlier, mathematicians typically identify outliers as any data items that are more than 3 standard deviations away from the mean. Now, in our data, 3 standard deviations would be a little bit less than 60, and the mean was 70, so an outlier would have to be around 10. Now, our smallest score was 27, so based on this statistical definition, we would not have any outliers. So our last topic here in statistics is something that you've maybe seen called the bell curve, or it's also referred to as the normal distribution. On large amounts of data, when you collect it, frequently if you distributed the data using a histogram, we would get a shape that looks like this, where this is the mean. Many of you will be taking the SAT test soon, and when you're comparing the SAT scores for all the students in the entire U.S., if we plotted all those scores, it would have this shape, as well as if we were collecting the heights of all, say, the adult men, say white adult men in the United States, and plotted their heights, that would also have this shape. Now, if you notice on the bottom here, we've got the mu stands for here is the mean, so that's the mean of the data, and we've counted off adding 1 standard deviation, adding 2 standard deviations, adding 3 standard deviations to the right, and subtracting multiples of standard deviations to the left. And no matter what the data is, if it's normally distributed, these percentages in terms of the amount of data that's in each interval is always the same. So you can see here about 68% of the data is always within 1 standard deviation, either below by 1 or above by 1. If we go from 2 standard deviations, that's 95% of the data. So only about 2.5% of the data on each end, or 5% of the data, is more than 2 standard deviations away. When we do our outliers that are out here, we're talking about a very small percentage of the data. Again, very rare cases. It's around, this number is about 0.15 or something percent. So it's a small percentage of a percent. Now we could use that to make estimates. So let's say I already talked about this. Let's say we know that the adult men in the U.S., by sampling or whatever, we've determined that the average or the mean height is 69 inches. And the standard deviation of that population is 2.75 inches. So if we wanted to know what percentage of men in the U.S. are 6 feet or taller, I've laid out here's our mean, 69, and then I've added 2.75, added another 2.75. So these are the boundaries on our percent curve. So 6 feet, 72 inches, so that's around here. So men that are 6 feet or taller are out in this part of the curve. They are bigger than one standard deviation away from the mean. This percentage out here adds up to about 16%. If we wanted to know what percentage of men are shorter than about 63.5 inches, that's 2 standard deviations away. So out here, that's about 2.2, or on some tables, these percentages, that would be about 2.5%. So again, we can kind of get an idea of the distribution of our data. So I hope this helps, and good luck with analyzing data. You see data on the news all the time, polls back in the presidential election, and now there's all kinds of polls and surveys about the gun control legislation, immigration legislation, etc. And the statisticians that analyze that data are using these measurements. So have a great day.
Are you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you